Hi guys, how are you doing? So I hope I hope you have read the question, at least this one, minimum reverse operation, which we'll be doing today. I hope I don't need to explain you the question. Please read the question if you have not yet, because that will be a waste of time in the video discussing the question. Okay, so basically we have to return the minimum number of reverse operations to bring the one to position I, right? That is fine. Okay, no issues. So let's say that we have this array 0 1 2 3 4, like this is the index, and we have 1 in this position. Okay, no one is banned right now, no one is banned. Okay, there is nothing banned till now in this. Like we are solving for a normal array, solving the question for a normal array. Okay, let's say k is equal to 3 in this case. Okay, what does k equal to 3 mean? We can select any subarray of length 3 and send this value to a certain value. Let's say 1 0 0 0 0 can be formed, or 0 0 0. We can take a subarray and reverse it. Like if we reverse this subarray of length k, then it will be 1 0 0. If we reverse this subarray of length k, it will be still 0 1 0. And if we reverse this subarray of length k, then it will be 0 0 1, right? Now if you check, if you see, let's say we are selecting this. Okay, 0 1 2, but the values are 0 1 1. Finally what happens is 1 0 0. So basically the value of 0 and 2 gets exchanged and 1 remains at its place, right? So basically we can say that 0 and 2 are connected. Like if I have a value at 1, if I have value 1 at 0, then in how many operations can I send it to 2? In one operation, because they are connected, right? In how many operations can you send it to 2? In one operation. So basically the weight is 1 of this graph from 0 to 2. And same, if I have some value, if I have this 1 at index 2, then I can send it to index 0 in one operation, right? So this is how we create a graph. Let's say in this case 0 to 2, 2 to 4, something like that. Why 2 to 4? Because 2 and, like, this is a k-length subarray, and we can when we can send this 1 to 4 in one operation, right? 1 can be connected to 3. Similarly, yeah, this is how 1 can be connected to 3 2 and all. So if now we start at position 2, we have, and all these edges are of weight 1. If we start at position 2, we have 1 over here. So what is the number of operations to send it over here? The minimum cost of the path to reach 0, right? So basically the minimum distance to reach 0 from 2, the minimum distance to reach 4 from 2 is also 1, and hence the number of operations required for 0 and 4 is 1, and all others we cannot reach using them, and this has a cost of 0, obviously, right? So basically we have to join. If we are not considering any ban, then what we do is we start at a I. We say that I'm discussing the brute approach now. We start at a I and end at k minus 1. Both of these should be in range, and what we do is we connect I, the node I, with node I plus k minus 1 with a weight of 1, edge weight of 1. Basically 1 we don't need to mention, because in normal BFS using that we can do it, because it's not exactly weighted. Like if 5 6 were values, then we should have used something else like by Dijkstra or something like that, but in this case we don't need to worry about that. Now I plus 1 should be connected with I plus k minus 2, right? I plus 1 should be connected with I plus k minus 2, I plus 2 should be connected with I plus k minus 3, and so on, right? Because if you consider a subarray with indexes 0 1 2 3 4 5 6, and you want to reverse this subarray of length 7, then you to reverse this with this, you connect this with this, you connect this with this, and this remains like connected to itself or something like that. So because we connect this with this, because you can send the value of 1 to 6 using one operation, you can send the value of 1 to 5 in one operation by reversing this whole subarray, right? So this is basically, we can connect all these values, so it will take k operations for each I, so n into k, so O of n into k plus the BFS of, okay, there can be n into k edges, so n into k, so basically O of n into k would be the time complexity if we are doing brute. This is for the brute, or O of n into k. Now let's optimize this. Okay, to optimize this we have to understand what values are I connected with. I is connected with either I plus k minus 1, okay, or I is connected with I plus k minus 3. How? Let's say I minus 1, our array starts from I minus 1, so till what it will go from I minus 1, I dot k elements basically will be I plus k minus 2. Okay, I plus k minus, if you count this will be k elements, so I, like I minus 1 will be connected with I plus k minus 2 and I will be connected with I plus k minus 3, right? I will be connected with I plus k minus 3, so I is connected with I plus k minus 3, I is connected with I plus k minus 1, and so on. If you check, you will see that I will be connected with I plus k minus 1, I will be connected with I plus k minus 2 when I starts at I minus 1, like when the subarray starts at I minus 1, when the subarray starts at I minus 2, this is 3, sorry, I plus k minus 5, and so on. So all these are odd basically, right? So when the subarray starts at I minus x, we can say then I is connected to I plus k minus 2x plus 1. Okay, you can put x equal to 0, you can see I minus k, I plus k minus 1. You can put x equal to 1, you can see I plus k minus 3, and so on, right? So if I is connected to x, if I is connected to I, like if our subarray starts at I minus x, then I is connected to I and I plus k minus 2x minus 1 is connected. Okay, now the question is how much can our x vary, like how much can our x be at max. So the question is, I first of all will apply, will say I minus k, I minus x should be greater than or equal to 0. We cannot go beyond that, right? So x should be less than or equal to I. This is obvious. Okay, this is our first condition. Second condition is our I plus k minus 2x minus 1 should be, our I plus k minus 2x minus 1 should be greater than or equal to I, right? This should be the case. No, wait, another condition will be I plus, like from I minus x we have to go k further, right? K lengths further, and this should be less than equal to n minus 1, right? So minus 1 cancels out, so x turns out to be I plus k minus n. So basically x range from I to I plus k minus n, right? This is one condition which I have written. Now I am actually finding out, I am trying to find out what are the values of I, like with which values I will be connected. Now also I forgot to tell, like you can see that these parities of these values is same, right? I minus 1, I minus 3, so parity of these values should be would be same, and hence will create a adjacency, will create a set of like values which have only you know values, will create a set in which only same parity values are there, right? So that is what we will do also, because from I you can go to a similar parity values only, you cannot go to all type of parity, right? So similar parity, and all of them are at a difference of 2, right? All of them are at a difference of 2, if you can see. I plus k minus 1. also we have to see that this is okay, this is fine. I plus k minus n, and also x is greater than equal to 0, that is fine, right? X is greater than equal to 0 and x is less than or equal to k minus 1. This is are you can you tell me why x is less than equal to k minus 1 and x is greater than equal to 0? X is greater than equal to 0 because we are saying a I minus x, so we are starting from I minus x, so x should be at, the x can be at max 0, right? That is true. And then why is it less than equal to k minus 1? Because I minus x and I should be in the same range. They cannot go outside, right? So, and at max they can be at a length at a length of k minus 1. So that is how. Now basically our range will boil down to maximum of I comma k minus 1 and minimum of 0 to I plus k minus n. This will our range be for x. Fine, that's okay. So for any I, we know that these are the ranges of values of x for which I should be connected to I plus k minus 2x minus 1, right? So if we put our x over here, the maximum x and the minimum x, then we'll get the maximum max range, like the left bound will be given by, let's say if we denote this by m1 and if we denote this by m2, then left bound will be I plus k minus 2 m1 minus 1 and I plus k minus 2 m2 minus m will be the right bound, right? So if we iterate from this to this, we know all these values are connected to I, right? If all these values are connected to I, then we can say that the distance, the number of operations to reach all these values should be equal to the distance to reach all these values. Let's say j, if we iterate over from j equal to L left bound, j less than equal to right bound, j plus equal to 2. If we say only if j is present in a set, which we will discuss, then distance of j will be equal to distance of I plus 1. This you get, right? Distance of j will be equal to distance of I plus 1. Fine, this is true. Now the question is, what will these values of j be? This j cannot be band, cannot be equal to any element in band, because bands cannot be reached, like we should not reach band, right? So we cannot. Also this j should not be equal to p, that is obvious. P is the starting element, and how is distance of p, because our starting position will be p in the BFS. That is all. And what else? Okay, so now I'll tell you how exactly will we iterate over this array, right? Like how will we go from this to this, like from left bound to right bound, how will we iterate? So initially what we did is we create a set S0 and S1, and we put all the even indices which are not band, and all the odd indices which are not band in this, right? And that's all. After that what we have done is we have started a BFS from point P, and now we are going to each value with the same parity. Let's say our left bound had some parity, so we start from that left bound and use the same parity and move on until our value is less than or equal to right bound. After that we break and we remove all the values from this set, because the reason being, because once they are reached, they are at the minimum position, because that is how PFS works, right? If you want to find the minimum distance in PFS, that is how it works. So this is how I have written that. So this is the formula which I derived over here, this right bound and left bound. And this is the parity, and for the same parity we move on and move on, and if it is greater then we break, or else we store the distance like this with the parent plus 1, we push it to the queue, and we erase it from the total set because it is already reached. So that is how we solve this question. I hope you understood the solution. If you didn't, you can ping it in the comment section below. Okay then, thank you.